E eu estou muito feliz de estar aqui hoje. Muito obrigado pelo convite, de mostrar um pouco da ciência que eu tenho feito aqui no grupo do Alan, na Universidade de Toronto, e o que eu vou também estar pensando em fazer com o meu próprio grupo na Carnegie Mellon. E eu vou ter que mudar agora para inglês, porque realmente eu não sei como falar desses assuntos em português, mas vocês podem fazer perguntas em português e eu vou tentar responder. Então, muito obrigado de novo. Thank you all for being here today. It's really a pleasure to have been invited to give this talk and to be here today. I'm so happy to share a little bit of the work that I've been doing in my postdoc, and also some of the ideas for the future in my own group at Carnegie Mellon University. And this talk is a comprehensive discovery platform for organophosphorus ligands catalysis. Is really a big effort that showed up recently as a preprint on Chem Archive, but I really need to and would love to start by thanking all the amazing people involved in this project, starting with Alan leading the Matter Lab, and then we have Robert Police, Dr. Shell Honor, that was also AstraZeneca, Akshat Nigan, who was an undergrad and now is a graduate student at Stanford in computer science, Théophile Godin, that is at IBM as well, and Michael Lindo-Daddario, graduate student in our group. And then finally, this is a massive collaboration that we did with the Sigmund group at University of Utah, who is part of the Center for Computer Assisted Synthesis, with Alan Peters, a graduate student in his group, Tobin Gensch, who is a co-first author and now a PI at TU Berlin. And finally, my great friend and collaborator, who was a postdoc in Alan's group, Pascal Friedrich, who is now a professor at the Karlsruhe Institute of Technology. And all of this is to say that, as Pierre mentioned, I've been thinking about solving problems with computers since 2008, really. And I think that there are at least two ways of learning chemistry with computers. One is a data-driven approach where nowadays we use machine learning and other techniques. And another is concepts-driven approach that in my PhD I explored immensely under Igor Alabugin studying stereotronic effects. But the reality, I believe, is that this is a loop, a cycle where you can learn both ways and they are not really to be separated. You can merge them. But the overall idea for my tenet, my philosophy in how we go forward is that we learn how to control chemical reactivity with computers. And, this all boils down to something that Pierre didn't say, but I will say that we were in a class in experimental physical organic chemistry, which wasn't that common around 2011, and he said the engineered catalysts are some of humanity's purest defiance against the relentlessness of entropy. Pierre likes to say these big things, and that really stuck with me after so many years. And yeah, it's kind of remarkable that us as humans and scientists can truly modify how we control the formation and breaking of chemical bonds, right? Nature had to evolve enzymes to do that in a very complex way, and yet we come here with learn how to do this with metals and so on. But all of this is to think about a major problem that we all have to think about and try to tackle, which is climate catastrophe, right? So if you go to Climate Action Tracker, you can see that if we continue on this path that we are at now, we might reach massive problems in terms of what to expect of human life on Earth. And when you think about a beautiful city like Rio, that it's in a tropical environment, that can be really a challenging way of view this. You could be underwater, and moreover, something that if you live in Rio, you know this very well, that climate change is turning cities into ovens, right? So we really want to do something about this. And I think that this comes in the form of a transformational wave in materials research. Barron's, which is this avenue in the Wall Street, has this idea of the three technologies that could create trillion-dollar markets over the next decade. One of the first one they mentioned is CRISPR-Cas9. Of course, that was the reason for the Nobel Prize in Chemistry in 2020, really well deserved on how we, as humanity, learned how to edit the very information that makes and shapes nature and us. The second one that Barron's mentioned is post-digital computing, where quantum computing plays a major role. And I would like to point out this paper in 2005 from my postdoc advisor, Alana Spurguzik in Science, showing the first idea in terms of simulating quantum chemistry on quantum computers, and took 15 years for Google AI to show a heart-to-fuck computation on a quantum computer. And finally, the third aspect of this is where I think we fall into, which is the into material sciences, and how catalysis can really play a role in this idea. And you have to, if I may remind you, catalysis is a massive part of the chemical enterprise, right? So of all industrial processes, 85% of them are catalytic, and of those, only 17% of those are homogeneous, and even lower, 3% of those are biocatalysis. And we are in a conundrum here, which is by 2050, we must achieve a total of 30% reduction in absolute CO2 emissions by the chemical industry, while going to this projected increasing demand of 180%. So we really have a challenge in our hands, especially thinking that 25% of all global energy consumption is used for producing chemicals, and that the chemical industry accounts for 7% of all greenhouse gas emissions, right? So clearly the problem is stated that we must try to do something in terms of catalysis. And what we need to do is develop better new catalysts for better industrial processes, more efficient ones. But we face a challenge here, which is from the concept to the discovery to the development of new catalytic reactions, it can take several months to years, right? So my question is, can computational chemistry, machine learning, and automation help us accelerate these timelines? Now, if you, for whatever reason, and there's no wrong answer here, heard of catalysis, and catalysis 101 in 3 seconds, I would say that the idea is that you start from a reactant and you want to go to a product, you have to cross an activation energy that given here is delta E double dagger that passes through a transition state. And the way that we want to think about this to make this reaction be more effective or faster is that you will employ a catalyst that will lower that activation energy and make this a more efficient, faster, easier process. So many of us in the field have been thinking about how to design catalysts and materials with machine learning. And my good friend, Dr. Robert Polici, and I wrote, together with Alana Spurguzik, wrote this perspective on how that would take place for trends in chemistry. And I think they liked it so much that we were invited for the cover of this special issue. But basically, design catalysts with machine learning is not a straight path. Like right now, we are in the era of descriptors and data swamps and humans performing experiments. I will tell a little bit about high-throughput virtual screening of machine learning, which is something that is embedded in the work that I will show you, and establishing data lakes. But we are approaching nowadays high-throughput experimentation and lab automation. The Spurguzik group really has been doing a lot on this field, and many others. And the idea is that we will arrive at self-driving labs and finally autonomous discovery. And of course, this all implies that we have to modernize the design, make, test, analyze cycle of research. In a conventional lab nowadays, you have a human that will make something and they'll test it and then analyze that, and you continues the cycle. But the way we want to go forward with self-driving labs is that you have optimizers using machine learning that send what next to be made to robots that will also analyze your samples, And finally, you have automated data analysis. That part was also where humans could contribute some more. If this all comes together, of course, with how to make things, chemistry is in the end an experimental science in many ways of thinking. And you have to think on how to make this robust enough in terms of high throughput experimentation and analysis. There's a lot of work to be done and being done by in terms of reaction digitization by people at IBM or the Cronin group at Glasgow. And you can also think in terms of microfluidics, like Carrie Humer at University of Connecticut. And finally, also very interesting ideas like smart servers. We here in the Programa group do have our own robot for performing parallel experimentation, which is a ChemSpeed robot. And we also collaborate with other groups that have one of those. And here's one running a ChemSpeed robot running ChemOS, which is this operational software developed by the Programa group to control robots and prepare campaigns to perform experiments. This one here, in collaboration with Merck and University of British Columbia, is a ChemOS controlled ChemSpeed performing a pretty challenging Suzuki coupling. If you want to know more about this, you can check our Chem Archive from our preprint on Chem Archive from last year. But basically, like we are also pushing the boundaries on this idea. And I want to say that, for the longest time as chemical scientists, we have been thinking in terms of direct design, which is you make a molecule or you think about a molecule and you perform an experiment or a simulation in terms of computations you can have. And that gives you certain properties of that molecule. But in the world we live in and how we want to make new discoveries and solve problems in a much faster pace, this won't do. We have to go through the idea of inverse design that can be done, for example, via high throughput virtual screening with filters, or more interestingly, I would say, is using optimization algorithms, evolutionary strategies, generative models like variational autoencoders, reinforcement learning, and so on. And this is what I'll be talking about. Because the idea of inverse design in the end is that you tell me the property that you want, and I'll tell you what that structure should be, right? So we are not bound to the structures anymore, we're bound to the properties that we need. And this comes very interestingly to how we think about these problems when it comes to designing and understanding and optimizing chemical reactions, right? Because for a given reaction, say A plus B that gives you C under a set of conditions, you can think of conditions in terms of continuous variables, and those would be time, temperature, concentrations, or discrete variables, which is which acid or base should I use, which transition metal should I use, which ligands should I use. For continuous variables, we are lucky enough to be able to use many powerful Bayesian optimizers like Phoenix and Griffin, developed again by the Programa group. Many other groups, including the Doyle group at Princeton, have developed amazing multi-objective Bayesian optimization solutions for organic synthesis. There's a paper from the Doyle group that showed up in Nature a few months ago. But when it comes to discrete variables, it's a much more challenging problem. And, when we go into optimizing ligands, I want to say that this can be a bottleneck for chemical discovery. Here's a paper from the Stoltz group at Caltech in Science 2019, where they're making these very complex natural products with potential anti-cancer drugs that it really takes a long time and a lot of human time and effort to be made. And you see that in the paper, they say, under these general conditions, we then performed a broad evaluation of more than 60 chiral ligands to achieve at least 80% EE, which in many ways, you think about this, is just appalling how much money and effort goes into this and how much time is taken from how we develop chemical reactions. And this is not just for highly complex systems. If we go back to a classic potentially one of the most used reactions in organic chemistry labs right now, the Suzuki cross-coupling, palladium catalyzed cross-couplings. In the classic Suzuki coupling, where you have your aryl halide plus aryl boronic acid with palladium, some base, and solvent. It's a very useful reaction to make, in this case, CC bonds. And you see that they use the ligand that is pretty ordinary, triphenylphosphine. Fast forward a few years to the work of Marty Burke at the University of Illinois Urbana-Champaign, and you see that now you have MIDA-protected boronic acid that you can do iterative cross-couplings, and that's how Marty Burke's group have developed the machine to perform these reactions in an automated fashion. You see that they had to optimize with a new ligand. And finally, just 1 year later, when they had a new idea on the slow release of boronic acids, again, yet a new ligand. And there are many groups, like the Buckle group, that have been releasing and developing for many years very complex designer ligands, as we call them. And in all of this all boils down to, for example, what takes forever for reactions to be found that you think are straightforward. Like in 2018, the Itami group showed in this paper in Science that if you take biphenyl haloarenes, they can be dimerized in an allylative fashion under a set of conditions, effectively making two new CC bonds and aromatizing the system in one plot. Very cool way to make graphene nanoribbon precursors. But the optimal conditions for these reactions involve ligands that is, not exactly the first thing that you would think, but also not too far out of what one would think. And moreover, something that chemists think a lot about, that has sometimes to tell computer science and folks thinking of in terms of machine learning aspect, is that optimal conditions for one reaction are not necessarily transferable. So here's an example in this Itami group's paper in Science, that they take 1,4-chlorotoluene, try to do a trimerization, so it will be much cooler to be able to make 3 new CC bonds from something as cheap and ordinary as this chlorotoluene. But the absolute best reaction they can get is using that ligand from before in the same conditions. It's only achieves 12% yield, and it's this plus an isomer. So really not ideal, right? And the Aspudagusi group have been thinking about using inverse design workflows with high throughput virtual screening for a while. As an example, they had the Harvard Clean Energy Project, where you start from a massive library generation of potential with potential fragments and then potential molecules that goes under machine learning predictions, quantum chemistry calculations, then all the way down to desired materials where you try to make devices from. So the question that I have is, how can we adapt these strategies to homogeneous catalysis and the development of these new catalysts? And it goes back to the phosphines that I was talking about. These are some of the most commonplace ligands in homogeneous catalysis. And like I showed you, optimizing them for your reaction can be extremely laborious, which ultimately hinders the progress in catalysis. But interestingly, phosphines are part of a vast chemical space that have many, many interesting properties and molecules, so they can be tuned for whatever problem you have. And many of them are commercially available as well, so that you can buy, or if not, make in a way that's not too difficult. So what we decided to do is we would build a comprehensive database of ligands, organophosphorus ligands, that we start with that vast chemical space I told you about, taking ligands that are commercially available, popular ligands in the literature, maybe not commercially available, but they are popular, that in the end gave us 1558 ligands as our starting point here. And what we wanted to do for this case is be able to extrapolate on these 1558 properties for the optimization of new reactions and new ligands. And for that, we need to build virtual libraries. And, let me tell you how we did this virtual libraries via combinatorial enumeration. We start with the 1558 ligands that we had in the initial set, we call a VL1. And from VL1, we developed a few ways on how to think about this, but basically we fragmentize these groups in order to get these ligands, in order to get 576 unique side groups that we then take in a combinatorial approach where we can have two of the same and one that's different to avoid chiral at phosphorus ligands, and we arrive at 330,000 potential ligands here, which, it's really an enormous expansion of the chemical space that we can explore in this case. And if we are a little bit more loose with our boundary conditions and be able to do a combinatorial approach for up to three different ligands, three different side groups, we can achieve 191 over 191 million possible ligands that we call VL3. So now we know how these virtual libraries will look like. Like we had that initial set of 1558 ligands, right? The way we had this organized at this point would be simply as SMILES strings. But molecules are not SMILES strings. Molecules are not graphs. Molecules are, these Lewis structures. Molecules are quantum mechanical three-dimensional objects. So I know that as an organic chemist, we like to think of molecules in terms of Lewis structures, and perhaps you are a little bit fancier and you're a computational chemist, you like to think of them as 3D structures. That's great because they are three-dimensional objects, and you go and render a ball and stick 3D structure. But in reality, these are not static objects either. They do have their own energy, and they are three-dimensional objects that wiggle on, like they will be moving around, right? So what is the relationship between molecular conformation, energy, and reactivity? Because remember, we are thinking in terms of catalysis, and these things really truly matter. Now, you can think of a molecule sitting on a point in a potential energy surface that I'm showing here as a local minima for a given conformer. That molecule will have many rotamers and be exploring the surroundings of that local minima. Finally, it may have enough energy to go through a transition state and arrive at a point in this potential energy surface that is a global minima, because very much like me, molecules are also pretty lazy. And the idea here, if you don't care, the too long didn't read message is that we must take conformational profiles into account when we design ligands and catalysts, okay? And this is important because this is how we're going to go for the next step, thinking about conformational ensembles of that 1558 ligands I told you earlier. The way we start here is that you have a ligand, and what we do first is perform a conformer search and generation using Stefan Grimme's GFN2XTB with Crest, also from Grimme. It's a free software. And then we get two sets of ligand conformer ensembles with and without nickel CO3 bound to that ligand. There are many reasons why we use nickel CO3 at this point as well, but rest assured that the idea is really to get some information that we couldn't otherwise. This is based on many ideas that Tolman have taught us through the years. So from this initial ligand conformer ensemble, they are done at the semi-empirical level with GFN2XTB. We need to think of a more robust conformer selection. And the way we do this is by sampling out low XTB energy conformers and steric extrema. Because when we think, again, in terms of catalysis, ligands will play a major role, and the way the ligands can adjust themselves around a catalytic system or reaction that's happening it's very important for what we're thinking about. The way we go about this is by taking a minimum and a maximum ligand size span. We use, in this case, a classic stereomol parameter to define that called B5. And we also take a delta in basically the difference between the lowest and the minimum and the maximum B5s. This denotes the fundamental steric extreme I was telling you about, and we also assume that the ligand can assume any accessible conformer within this range. Another way that we think about this is by taking a Boltzmann weighted conformers average that is a representative value for the entire ensemble. This is more in line with what I believe we would think to do first. And finally, we also take the conformer with the smallest Borel volume, which is to represent sterically congested complexes when you go into catalysis, which again is something that's very important and show up in a preprint recently from Doyle and Stigma groups in Chem Archive. We then perform DFT evaluations on each of these conformers. I'm not going to go into the details on how we do this, but rest assured, there's a lot of calculations that were performed for us to arrive at representative conformer ensembles that are what we use to go to our next steps. To be precise, what we have is 2,437 unique conformers from those 1558 ligands that I told you about, with an average of 13.8 conformers per ligand being calculated here. Now, having all of these conformers is great, but what can we do with it, right? We would like to have properties, and that's the next step in our workflow. Because remember, in the end, we want to expand, right? We need to build machine learning models, and other the sing-song of Frozen, do you want to build this? So like you can think of, do you want to build machine learning models, which you're going to need to gather some descriptors. We'll start with those 1558 ligands that I told you about, with all of those 21,000 unique conformers. But the question is, which descriptor should I get and how, right? Well, how do you describe a ligand will define which descriptors you should get? And this is an easier question than how at first, because basically from many years of studies in catalysis, physical organic chemistry, we know that there are at least three classes of parameters that are important: electronic, steric, and whole molecule parameters. And in our case, we had 38 electronic, 28 steric, and 12 whole molecule, giving us a total of 78 properties for each conformer here. So we have the 78 properties I evaluated for each conformer in the representative ensembles. In terms of electronic parameters, we have things like NMR tensors or Fukui functions and NBO, natural bond orbital analysis. Sterics, we have classic stereomols and Bird volume. And for whole molecule, we have things like dipole moment, energy salvation, and developed by Robert Police, the dispersion potential pint. But, the next question is how? This can become a project on its own, a massive one, in fact, that will be a lot of work for any one person trying to do it by hand. And the way we thought about this is that the truth you seek is in the matrix, meaning that we developed, and this is led by my great friend, collaborator, and Dr. Shell Yorner. There was a postdoc at AstraZeneca UK, and I was a postdoc with us here in Toronto, that we developed Morpheus, which stands for molecular features for machine learning, that can help you gather electronic, steric, and some of whole molecule parameters automatically, very easily. In fact, you can go to GitHub right now, download Morpheus and play with it, and you see that is really well documented and super easy to use. And it's a truly remarkable tool if you want to have features for training machine learning models in chemistry. Now, okay, so we have this now 190 descriptors for each ligand here. So let me give you a summary of what we've done so far, right? So we started with 1558. We broke it down, fragmented into unique substitutes that led us to combinatorial enumerations forming VL2 and VL3, 330,000 ligands, and up to 191 million ligands. But now next we want to be able to understand them because we have all of these properties. The question is like, what does this look like? I'm still a human, and I would love to try to understand this in a more visual way. There are many ways you can think about this. There are many ways that you can compress dimensionality and use dimensionality reduction techniques. One that is common is using principal component analysis. And what we see here is that you can label these in terms of what is attached to phosphorus so that it's a little bit easier for you to identify and try to learn what goes on to this chemical space. What we see is that the first principal component is related to sterics. The second is related to electronics. If PCA is not the proper tool for you to identify the ligands that you're looking for, you can use different techniques such as UMAP. And you can see that the shape of the chemical space is a little bit different. I'm not going to go into details of this because I will show you how this is actually interactive later. But the idea is that we can use these types of techniques to shape the chemical space and try to learn more about it and use it for applications. This finally leads us to how to expand these, right? And the idea is to use machine learning predictions. So the question is, how do we go from 1558 to 191 million ligands? Well, some might say, throw this black box called machine learning on it. And some other might say, how do you achieve these arcane magics to do this expansion, right? Well, it's not a black box, and I'll tell you a few things about how we went into this adventure in machine learning. Starting with a new way to think about how we define molecules in this problem. This was led by and developed by Tobias Gensch, and the idea is the BOS stands for bag of substituents. Well, you have essentially, my pointer is not working well. But if you look here, the idea is that the first ligand has two of those blue substituents that are the same. So you point that as two in this matrix, has none of the yellow one and one of the red one. And then next ligand has two of the red ones, no yellow ones, one blue one, and so on. But the idea really is that you perform a linear regression of some type where a descriptor can be defined as a constant plus the weighted sum of each of those substituents times the weight of that substance. And I will show you some results for how well this performs. But again, I said before, you can think of molecules and their representation in many different ways. Another way that's quite common in machine learning for chemistry is thinking about them in terms of fingerprints, which I could just summarize as thinking about that you can transform your molecule into a barcode. Of course, it's more complex than that. But this allows for us to use techniques such as multiple linear regression. You start simple. It's great to start simple for you to have a baseline and progressively go to more complex models such as random forests or Gaussian processes employing Bayesian techniques. And finally, you can also use things like gradient boosting regression, kernel ridge regression, and so on. One last type of representation and therefore models that we tend to think about is graphs. And you can think of molecules as graphs. So you go from a Lewis structure to a molecular graph. Basically, each atom in your Lewis structure corresponds to a node, and each bond corresponds to an edge. And graph convolution neural networks on molecules have been shown to be extremely powerful and quite useful, being able to, for example, enable computers to learn what to predict smells and odor. This is a paper in arXiv, and also you can check this Google AI blog post that Benjamin Sanchez-Langlin and Jennifer Wade that were in Alan's group, and also Alan participated, in this work on machine learning for scent. They use graph convolution neural networks. There are many other interesting works on this theme. You can see two seminal papers on this field, one from the Google Brain team on neural message passing from quantum chemistry from 2017 that has over 1,700 citations. And also, prior to that, a paper from Rafa Gomes Bondarelli, David Duvenal, Alon Asperguzik, and Ryan Adams on convolution networks and graph for learning molecular fingerprints. Again, also 1,700 citations. This is not to show you, these are very useful. This is a very useful technique. And we applied that here, graph neural networks. And what I have on the left here is basically the idea that we take calculated and predicted with our models. So let me show you some results. The first I want to show is the energy of reduction in the Boltzmann ensemble, and our models perform very well, have an R-squared of 95 and a mean absolute error of 0.01. Excellent. Let's go to another one like FMO for frontier molecular orbitals. The energy for the Luhmann, the Boltzmann case is also quite good. Same statistics basically, and we can go to, for example, whole molecule properties like pint. We still have excellent results, and even also here showing you for the HOMO energy on the right is still quite good in terms of R squared. Let's switch to something to like descriptors in terms of sterics, like sterimol B5 and B1 and L. It's still pretty good. It's still very, we can still use these predictions. But then we get to a few not so great predictions like pyramidalization on phosphorus. Start to see results that are not ideal. Low R squareds. Same goes with buried volume on this minimum delta. But maybe there's something we can do about this. Continue on all of these models we have with GCNNs. We can get to situations where we basically have catastrophically bad results, like this buried volume here in the Boltzmann section, which is just garbage. And even other ones that are even worse. And it's sad because these CNNs were supposed to bring balance to the forest. But I'm telling you this because there is not one model out of all the models we explored that performs well for every single property. Models will have different strengths to different things that you're trying to predict. So GCNNs, like I'm showing you here, can be quite good for energy of reduction and totally terrible for that buried volume from far, etc. And just showing you as examples of how we think about this, taking a property that is so pretty well behaved for most models that I'm showing here in terms of Vimy and Boltzmann, you can see that some models like Beggar substance performs best than everything else, and our graph convolution neural networks not so good, and so on with Gaussian processes. Which is to say that one model alone is not good enough. It just isn't. But we thought about this quite a bit, and we arrived at a solution, which is models of models, the idea of meta models. This is not a new idea, of course. Many other people have done this, and I wanted to show you what happened in our situation. We take these machine learning models and think of them as listening to this song from the Beatles, "A Little Help from My Friends," right? Like what they help each other correct their biases and errors to form a model that is more robust. What we do is use stacked regressions for these. And we think of this as a platform for robust meta models. Long story short, I'm not going to tell you all the math and the ideas that go into formulating this. I can show you the average contribution of each model type to all the meta models, or it's GCNN with about 21% and gradient boosting regression with 20%. But we see here the Beggar substance, which is a great model. It's interpretable with 16%, which is, well, almost 17, which is quite reasonable. And if you look at the how these models perform in the end, you see that the meta models have a average mean absolute error in the test split in the test set of 0.245 in standard deviations, and you can see that is lower than any of the other models on their own. So I asked you, how would we go from 1558 ligands to over 191 million ligands? And I told you that we could think about these in terms of using these meta models. But there is a caveat here, which is it's just too expensive for us to do this on the fly for what we want to do next. Because when we envisioned this, we wanted something for the community to use to learn and develop their own reactions. And that would not be possible if we're just going to give you a bunch of files so that you can try to figure out what's going on. So we take a step back and go through VL2 first, and I'll show you why in a second. So just closing this cycle, we were able to use machine learning predictions to enhance these virtual libraries, right? And this all comes down to Kraken, this little guy here who is our friend, and I will try to do a live demo of Kraken right now. Let's hope that nothing is going to fail me. So let me change what is going to be shown to show you what Kraken looks like. This is open. All of you can go and use right now. It's kraken.cs.toronto.edu. And as you can see here, this is our UMAP representation. You can hover over each of these points and you will have a ligand. These are the initial 1558 ligands. If I want to, I can make this map denser by adding some of the machine learning data points or not. Let's remove them. If you say, well, you know, the way I'm performing my chemical space search, I cannot have anything that has fluorines connected to phosphorus, and I would prefer not to have anything that has 3 nitrogens connected to phosphorus. You can remove them. And, you know, I want to see this actually as a PCA. No problem. You can just click there. And let's pick a ligand. I'm going to pick something totally at random, but I want to pick something cool. This, I don't know. So when you click on it, you see that you have information about that ligand. Here's a link to go to PubChem that you can just click on. You know, it takes you to PubChem, the PubChem page for this. And there's some PubChem data here as well. All the properties I told you about are here, all 190 of them. And you can also see the conformers and play with them in 3 dimensions to see how you can think how this is going to fit in your catalytic pocket and so on. And you can see the other conformers for these molecules as well. And you can also just download a file that has all of this information for this ligand for you like that. And another way that you can go about this is by searching, by drawing what the ligand you're looking for would look like in a pretty straightforward way. So you can just, you know, pick up phosphorus, and then you, let's say I'm going to put 3 things here. I'm going to put cyclopentyl, and I'm going to put 2 phenyl groups. By the way, I never done this one exactly before, so I have no idea what's going to show up. Things that are somewhat similar to this one particular ligand present here, and you can click on them and see their properties. This is a machine learning one, so there's no not necessarily PubChem data or oh, sorry, but you know, you can also see the conformers for it. Yeah, so this is Kraken. Like I said, it's open. You can go and use it right now. And let's go back and finish this talk, shall we? coming back. So what can we use this for, right? Let me tell you a very quick story. These two papers, one from the Bark-Biscoe group in Science in 2018, and this one on the right from the Burke group in Nature Communications 2019, they have two very similar reactions. You can think of them. I'll tell you more details in a sec, but basically they have two very similar ways of transforming an alkyl chain connected to a boron that can be a boronic acid or boronic salt, and using palladium and a set of ligands, they achieve sterol retention. And the very cool thing about these two works is that the set of ligands that they used was completely different from each other. The question is, can Kraken enable the transfer learning of reaction outcomes between the two? And like going back to saying what these reactions look like, we have your alkyl chain with a boron connected to it, going through a set of reaction conditions. There's some organophosphorus ligands that you achieve sterol retention. Burke use ligands with motifs that look like this one in blue on the top right, that are the most selective ones are electron poor orthomethyl aryl orthobenzyl aryl phosphines, and Biscoe on the bottom middle bottom here used in red used ligands that are more in line with classic Buckle ligands, where you substitute the cyclohexyl group for one of these arrow groups. So what we can do is cross predictions between the data sets. If you train a linear model here, what we see is the best ligands that from the Biscoe work, or molecules that would look like the design from the Biscoe work, would perform very well in the Burke's data and the Burke's reaction. And similarly, we can have molecules that look a lot like the set that the Burke group used would perform very well in the case of the Biscoe's reaction, the one in science. But you can do much more than just cross predictions between data sets. You can use that virtual machine learning enhanced chemical space to perform predictions based on selectivity. But so each pixel that you're seeing here in gray is a ligand that is thought of in terms of machine learning, basically those machine learning predictions, and we can find candidates that are surrounding that Burke and Biscoe data space with that predictive selectivity I told you about. But you can also search through these dense chemical spaces based on descriptor space vicinity. So you have the ligands that perform well, that we know that perform well, and then you can search for other similar ligands around this space, effectively reducing the amount of experimental evaluations one would need to perform in order to find what's the best ligand for their reaction that they would be developing. So, like I said, Kraken is open database that any and all of you can access for free on kraken.cs.toronto.edu. If you want to read the details on this paper, please check out Chem Archive with this tiny url.com Kraken-paper. And I want to say one last thing, that I think it's high time for chemistry and chemical engineering to take a page from the information revolution. This is from an opinion piece that Walter Isaacson, the writer that wrote amazing biographies for many influential people, including this last one on Jennifer Doudna, said, "It is another wondrous miracle from a biotech revolution in which knowledge of genetic coding will become as important as digital coding, and molecules will become the new microchips." And I see this as, for us, chemical scientists, chemical engineers, to take that and really think how we are going to tackle the problems that we're facing for the next decades. We must take into account all of these new techniques and try to use it to speed up the process of research and development. And I think that this generation really will be the one that will think of molecules as new microchips for control of chemical reactions and possibly digital computing. And I see this as, with a future really full of possibilities. I think it's ahead of us. And of course, I'm saying that with the idea that the Gomes group will start at Carnegie Mellon University in January 2022 in the departments of chemistry and chemical engineering. We are chemical designers, engineers, and data scientists, where we are going to use artificial intelligence, computer science, computational chemistry, and automated flow synthesis, and many other automated experimentation techniques to develop and understand catalysis and new reactions, new organic materials, all of this, of course, always with physical organic chemistry in mind. So you feel free to reach out to me on my email or on Twitter. Let me thank again the amazing people that were involved in this project, in the Sigma group and in the Aspuruguzi group. I cannot stress enough how amazing these people are as researchers and as friends, and also the Matter Lab led by Alona Aspuruguzi here at University of Toronto and Vector Institute for Artificial Intelligence. I would like to thank Bunty for providing my fellowship in the group, many of the funding agencies, and you all for listening. Thank you so much. Obrigado.
Parabéns, Gabriel.
Obrigado.
Parabéns, Gabriel. Impressionante. Realmente, parabéns. Muito resultados da sua posição, os seus objetivos, os seus resultados, né? Muito merecidos e tem orgulho, né? Até para o UFRJ. Parabéns. Eu vou abrir agora o espaço para as perguntas. Tem várias perguntas que já foram escritas aqui no chat. Eu gostaria de convidar as pessoas para se manifestarem, né? Além do chat, você poderia falar assim, falando, abrindo o microfone e fazendo perguntas para o Gabriel.
Let me just say, and I'll say this in English. I think there are people watching on YouTube that do not speak Portuguese. So if you have questions and you want to ask in Portuguese, I would also, translate it.
No, sorry.
No, but all right. Happy to answer any questions you have.
Can I ask first?
Okay. Bye, Bruno.
Okay. First, I want to thank you for your presentation. I think it was really insightful. I personally am very interested in this world of chemical AI. And I work in my project, I work really close with the industry, but the cosmetic industry and the final product industry. And I've always thought to myself of different ways to bring this sort of AI to optimize the end product. Because I think, I know you're working here with catalysts and chemical reactions, but I wanted to know if this is possible for things such as polymers or like physical interactions for the final product, and how can I, as a person that's interested in the topic, learn more and try to build a knowledge and this sort of stuff.
Yeah, Bruna, I'm gonna answer in English. So, thanks for your words, and thanks for being here. And yeah, so it's a great question, right? So you're thinking, can these be used for different, basically in your idea for cosmetics? What you're trying to do is optimizing for a different type of objective function. There are many ways of thinking in terms of optimization these days. We use Bayesian optimization for many reasons that I unfortunately don't have the time to go through here. But the main question that will come down is like, oh, like you may want to use machine learning, but the reason is why. First of all, you have to think, why would you want to do that? And the second question is, do you have a data set that is, or can you construct a data set that would be sufficiently robust for you to use these techniques for, right? So those are things that you have to have in mind when you go up about it. And when it comes to materials, it's very cool how this field is very open and friendly to newcomers, and it really is a field that you can learn a lot by going through other people's codes, and there are many trainings online. So we can talk more about that if you would like to on a one-on-one. But
absolutely. Yeah, 100%.
Yeah. Nice.
Okay.
Mônica, you can. Você pode perguntar em português e eu traduzo e tento responder.
Ok. Eu falei para o pessoal que está acompanhando pelo YouTube de se manifestar pelo chat do YouTube. Né? Na nossa sala aqui, só tem os alunos da pós-graduação em Química. Então, eu acho que eu daria um espaço para fazer perguntas ao vivo para os alunos, né? E depois, uma vez que essas perguntas tiverem sido respondidas, eu vou apresentar as perguntas do pessoal do YouTube.
Ok.
Então, Mônica, se quiser fazer a pergunta em português, pode falar.
To calculate and optimize all of the ligands and all of their different many of their conformers. That's how we were able to rank and evaluate those conformers. The 78 descriptors that we talked about are in the paper, and it would be impossible for me to go through them here, but I can say that you can use Morpheus, which is on GitHub, Shell Yarner's GitHub. Right now, you can go and use them to get many of those descriptors. The last question that she asked was if the software we use for ML was in Python. Yes, and if it's free, and it's also yes. We used only open source stuff. So for some things we use PyTorch. For some other things we use TensorFlow and Keras, and for other things we use scikit-learn. So it really depends on what exactly you're talking about. But everything is free and open, and you'll be able to replicate it all with once we put it on the GitHub. Though, yeah, I hope that answered your questions.
Thank you, Gabriel. Beatriz?
Olá. Hi, Professor. Thank you for your presentation. I think it's very interesting how you can think in so experimental science like chemistry in terms of mathematical predictions. So I think your presentation was really, really interesting. And my question is about how accurate need to be your approximation in the FT calculations to make a good databases, because for something properties you can use local approximation and have good data, but in other you need to use something more computational expensive, like non-local approximations. And I wonder if you need to be divide your properties to make this huge database, or you can use okay, I have a supercomputer, so I will use only hybrid orbitals to calculate all of my properties.
Yeah, that's a very good question. You know, there are layers. If we were to do something that, for example, multi-reference character, you need to use computational methods that take that into account. And of course, like you said, that is computationally can be computationally very expensive. So we are dealing with a problem here in this case that have that kind of problem, or doesn't have that kind of multi-reference character. Therefore, when we go about this, we can use simple-ish hybrid DFT for most of the properties that we want to have. And we also use a lot of semi-empirical methods. And moreover, one of the things that you have in mind here is that because of the way we are thinking in terms of these problems, many of the properties are in relationship to each ligand and molecules on their own. Therefore, there are some things that we can waive in terms of how perfect and accurate the computations are. And as in life, when you are trying to do something, or of a project of this size, there's a trade-off between accuracy and volume and speed. And we want to solve problems. What I mean by this is real problems that will help a medicinal chemist figure out what's the next reaction that they should use for making the next antiviral drug. So, in that case, we cannot afford to spend a lot of time doing, insanely high level computations that would not add more information than what we need. But as with everything in life, we need to know what we're doing in order to do that. And that is a trade-off that we are always thinking about and always taking into consideration before we do anything. So it's not a blind search. Excellent question. I really, really appreciate it.
Thank you.
Thank you.
I have another question. I don't know if I can ask you again or we can.
Maybe.
Okay.
Well, okay, go ask it. There are several ones. Okay, go for it.
Okay. This is nothing about other calculation question. It's like in the beginning of the presentation, you're talking that this calculation can be very helpful to catalysis. Né? And I'm thinking if you have a heterogeneous catalysis, normally you have a big, high temperature in your reactor. And I don't know, really make difference if you have a high temperature and a high energy for all that molecules have really difference between the conformation of the molecule. This is a case you can use this kind of data sets will be really different for some reaction in this case, or I can use for other things. This case will be some difference.
Yeah, so that's again another excellent question. I assume you are interested in physical chemistry or maybe chemical engineering, but the idea here is that when you go to high temperatures, of course, you have to think that your Boltzmann weights will change. That's one thing, but everything that I talked about is thinking in terms of homogeneous catalysis. Okay, for heterogeneous catalysis, you really should check the work of my soon-to-be colleague Zachary Ulysses at Carnegie Mellon Chemical Engineering, who has been doing amazing work on heterogeneous catalysis and machine learning. And they have a project where it's an open catalyst database. They partnered up with Facebook AI research team, where they are doing similar things for heterogeneous catalysts and so on. But it's again a great idea. I hope you think about applying for a PhD at Carnegie Mellon.
Thank you.
Okay, you got one PhD candidate now. Okay, Yeldicia, would you like to ask a question?
Ok, professor. Boa tarde e parabéns pela palestra. Eu fiquei um pouco em dúvida em relação a determinada slide que tinha um composto com fósforo e o outro com fósforo e níquel. E eu percebi que parece que você fez uma comparação entre os dois compostos e parece que o composto com fósforo foi escolhido em relação ao composto com fósforo e níquel. Daí eu pensei, será que é devido à geometria desse composto? Talvez o composto que tinha fósforo e níquel já de alguma forma poderia prejudicar na interação, ou poderia haver algum tipo de distorção na geometria dessa molécula?
Obrigado, Lúcia, pela pergunta. So, Lúcia asked why did I show a situation where I had the organophosphorus ligands isolated or bound to nickel CO3? And the reason is because we wanted to get some properties, for example, Cohn angle, that come from when you have your ligand complex to a metal center, in this case, we chose a classic that's being used forever, which is nickel CO3. There's no other reason, because we're really just interested in how the organophosphorus ligands would behave. So the next steps do not involve calculations with nickel CO3 just at that point, because the information we needed was could be obtained at that point. So that's all it is. There's nothing special about it.
Obrigada, professor.
Obrigado, Gabriel. Então temos a última pergunta dos nossos alunos, Matheus.
Olá, professor. Boa tarde. Boa tarde a todos. Deixa eu ligar a câmera aqui. Tá, enquanto liga a câmera, professor, eu vou fazer a pergunta bem rápida. Primeiramente, obrigado pela apresentação, eu achei muito interessante. Realmente é muito desafiador nessa área. Eu gostaria de perguntar como, não sei se o senhor chegou a falar disso, mas não ficou muito claro para mim, como o senhor escolhe o método de machine learning que você vai utilizar, se é um método supervisionado e não supervisionado. E no caso da utilização de métodos supervisionados, quais são as entradas, os parâmetros que o senhor geralmente utiliza para fazer esses cálculos e essas predições?
Okay. Mateus, thanks for your question. And his question was if we use supervised or unsupervised learning techniques for this work, and if so, what were our inputs for those models? If you're specifically talking about predictions, yes, they were supervised learning techniques. You may have seen them. I showed that thinking in terms of representation. So number one was the bag of pseudostudents, which is a new idea developed by my friend Tobias Gensch. The second one was using fingerprints, and I'm saying the representations as the inputs as well. And the third was graphs. So that's, that's basically the idea for the supervised models. Some may say that the dimensionality reduction techniques are unsupervised ones. If you can also think of that way, but that's basically it. There is nothing too crazy about it here, other than how to do this well with chemistry. And luckily, this is something that the Spurguzi group really have been developing for many years now, and one of the reasons why I joined, I wanted to do my postdoc with them. Does that answer your question?
Sim, respondeu sim, professor. Mas aí, na hora de escolher entre regressão ou até rede neural, como você faz essa escolha?
Mateus, that's like, how do we choose which models to use, right? And if this is the whole point why we use meta models, because in the end, what we observed after training and testing many different models and hyperparameters and so on, we observed that there is not a single model, and that's okay, actually, that's performed well across the whole 190 descriptors. So instead of choosing one or another model, we decided to use stacked regressions, where you take all models and stack them and train them together in a way that you can alleviate the bias of one model with the other ones. Details are really in the paper, and it's a bit more complex than what I'm saying here, but the idea is that you avoid having to choose a single model, basically.
Ok, muito obrigado, professor.
Thank you.
Alessandra?
Oi, olá, deixa eu abrir aqui rapidinho a câmera. Uma pergunta bem rápida. Assim, no caso de isômeros, o programa ele é muito certeiro ou ele dá uma aproximação, assim, uma porcentagem?
Alessandra asked, like, in case of isomers, what do you mean? What do you mean? O que você quer dizer com isômeros aqui?
Sobre, assim, quando nós temos isômeros, ele é muito certeiro com o isômero, assim, tem uma porcentagem na livraria, assim, uma porcentagem, ele consegue detectar um dos isômeros de forma certeira? Não sei se eu consegui me expressar bem.
está perguntando se, no caso das aplicações no final que eu mostrei, se qual dos isômeros que você queria escolher?
Isso, porcentagem.
Okay, so Alessandra is asking, in the case of the applications in the end that I showed you, that we could use Kraken to do cross predictions or predictions, cross predictions between two reaction data sets, what would happen? And if
Krakens.
How precise that is to choose between two stereoisomers. It would be as precise as the models that we trained previously, the linear models. And those, of course, are trained, in this case, on experimental data. So, like it really is not a feature of Kraken itself, but rather the other predictive models that were that can be used for certain reactions. This work that the Sigma group especially have been doing very well for the past 15 years or so, I'd say, being able to achieve very robust predictions in terms of financial selectivity. So it really, I would say, of course, there will be, there can be problems that escape how we build these models, but overall, I would say that this is a little bit out of scope on how we were thinking about this, if that makes sense. But it works, I would say, yeah.
Thank you.
Thanks for the question.
Thank you, Gabriel. So let's close our question time with Professor Pierre.
Gabriel, deixa eu fazer um comentário e a minha pergunta, né? O Hammett, né, foi o cara que inaugura a físico-química orgânica quando ele substitui substituinte de um anel aromático por um número, né, que é o sigma, né, que é a diferença de acidez de ácidos benzoicos. De certa forma, ele traduz estrutura em um escalar, em um número, né? Uhum. E aí você tem uma variável que você controla, que você pode botar no eixo X, e você vê com uma determinada propriedade. Por exemplo, velocidade relativa de uma reação está em Y. Né? Isso abre o QSPR, ou QSAR, né, para o pessoal de farmacologia. Né? De certa forma, eu estava pensando aqui nessa coisa de programação, né? A pergunta tem a ver um pouco com isso. Né? Quer dizer, o segredo está como é que você codifica estrutura química em vetores, né, na tua matriz. Aí, ele usou um único escalar, foi bem inteligente. Depois a gente está tornando isso agora um vetor num espaço aí que é de maior ordem, né? E aí eu estava pensando assim, você vê, né, a gente tem programação orientada por objetos, né? Isso é um avanço nas técnicas de programação de computador. E eu vi em algum lugar que o pessoal estava tentando fazer códigos para os computadores escrever eles próprios programas, quer dizer, será que você consegue fazer um programa de escrever programas? Quer dizer, você pode fazer um programa que você diz o que você quer, você dá o objetivo de um programa de computador, ele fazer o que você quer, te ajudar a fazer alguma coisa, certo? Então você teria algoritmos que tentam codificar um programa para fazer o que você quer. Que é mais ou menos o que a gente está tentando fazer, né? Porque química já é orientado por objeto, o nome desse objeto chama-se átomos. Então, então, será que existe algum paralelo, quer dizer, numa química orientada por objetos, né, em que você pode codificar propriedades? Será que a gente está indo para o Química 4.0? Né? Será, quer dizer, existe alguma iniciativa? Quer dizer, eu sei que existe, basicamente, vocês estão vendo essa coisa de programas que codificam programas, você precisa de um computador. Será que você pode usar essa inspiração para trazer essa coisa da química orientada por objetos, que já é orientado por objetos, né? A gente só quer, na verdade, que escalar e representa. Será que a gente precisa representar o átomo? Eu quero fazer esse paralelo entre programação orientada por objetos contra química orientada por objetos, e quais seriam objetos, esses objetos. Essa eu
PR's questions, like, as always, a big thinker. Basically, would there be a parallel between object-oriented programming and chemistry? So would be a chemistry-oriented, object-oriented chemistry. And the object here will be the atoms. Yeah, that is really cool. Like now, I would say that there are people, of course, thinking in terms of how to make machine learning models, taking more atomic potentials and properties, right? So you have my future colleague Alexander Isayev and Anakin on that idea. Very interesting models. You have SOAP and everything that Michele Teriotti has been doing, and also I cannot forget Anatole von Liverfield as well. So I haven't heard this analogy before, to be honest, but I can see how it makes sense. It could make sense. I'm puzzled. I have to think about it.
Obrigado.
Obrigado, Gabriel. Acho que temos mais uma. Momento.
Não teve perguntas do YouTube?
Não.
Ok.
O Rafael, vai.
Oh, hi. So my question is that all your data and also even the data that you created through predictions and models, those are all somehow based on previous experiments at some point, right? And my question is more like, if you will start only making chemistry based on predictions and those models, there is the possibility that those models are not going to be updated with new data and new discoveries, and we may fall in some kind of local minimum because there is nobody's trying something really new. They're just going to go with the result of the programs and what should be predicted as the best option. So
right. So, sorry. Go ahead.
Yeah. So I see like the great potential with machine learning and chemistry, but at the same time, that's always something that, I get like, why should we just follow what the machine learning is telling us to do and not just try something new, something that came to our mind and so on?
Well, because so like that's a very important point. Okay, so I appreciate that you asked this question. First of all, the only thing that we had in this case that was based on previous data was in the end to be able to do cross prediction between data sets and expand around that virtual database, but like a virtual space. So you have to remember that what we did here was predicting things that were not used experimentally at all, first of all. Second of all, you are absolutely correct. If you are to do something that can only do interpolation, how can you ever discover something new? That is a complex question, because in principle you can. There are many things that even though they're within interpolation, they have never been tried or even predicted for, because we never thought about them, or just are things that you wouldn't buy, and this is or even like try to make. So these are points within it. But we can and have many ways of going and using generative models and things that can explore rather than exploit virtual spaces and so on. So I have worked on ideas using genetic algorithms. Many others have worked on the generative adversarial networks, or reinforcement learning can also be an interesting approach here, or variation autoencoders. So there's a whole plethora of algorithms and ideas for exploring rather than exploiting that would take you out of that local minimum that you mentioned of, like data that you are around that. Excellent question. And of course, it's also a problem that folks in machine learning development, machine learning theory are working on too. That should not prevent chemical science, chemical engineering from using these techniques for solving problems that they have at hand at that moment. In fact, it should empower us to try to make contributions to these fields too.
Thank you.
So I think we are done here. Thank you very much, Gabriel. Actually, I have a curiosity, which is not strictly related with your results, but with them, let's say, teaching methodology. I mean, you are working with, let's say, what is one very promising branches of chemistry. Okay, something which I will invest in if I were a research entity. Okay, both private or public. So your research, in my opinion, is something which will endure in time. On the other hand, your research is the perfect, in my opinion, example of what this is. What's the word? The union of two different scientific fields. I mean, you are multidisciplinary. Okay, you are a clear example of that. And so I would like to ask you, since you are going to be a professor, someone who will not only discover new things and find results and publish articles and produce patents, but you will you will raise new sciences. Do you believe that the division between chemistry, computer science, is going to be reviewed in any time from the point of view of university? I mean, you are a chemical student, you're a student of chemistry, or you're a student of computer learning, or something like that. Do you believe that any new kind of course is going to happen? I don't know, be creative.
Well, I think that. Well, I think that diversity of thought is important, and people coming from different perspectives is very important to solve problems. When it comes to teaching and preparing the workforce, this is something I think about quite a bit. And I'm very happy that CMU took me in and will be taking me in, because they do have a strong idea and thoughts in terms of automated sciences, and there's a new master's program at CMU that is in data analytics for physical sciences. And in fact, CMU also has, for the long time, a PhD in chemical engineering. You can also obtain a master's in computer science within it. So there's a lot of venues where these things can overlap and go. Right. So, I mean, I think that many of the things that we're talking about here, that I talked about here, are going to be fundamental building blocks in the education of the next generation. I honestly do not see how chemical scientists will go forward without using machine learning and programming in their careers. And I'm not just saying computational chemists. I'm talking about anyone doing chemistry will be using these tenets in their lives, in the lab or otherwise. But I don't know if like these ideas of merging everything under one umbrella will take place. Maybe it will. I don't know. I just don't know. What I do know is that myself and many others here in Canada, in the US, and at Carnegie Mellon are thinking very hard about how we're going to be training the next generation, preparing them for how chemistry and the future of manufacturing really is going to take place. Especially the US has been, like with this new administration, thinking a lot about this, which is great. And finally, organic chemistry, as we were all taught, can be kind of boring and really repetitive, and like there's a lot of memorization that's all unnecessary. One of the cool things when I was a student with Pierre on my very first semester was that he came to the room and said, all the chemistry is inside this equation, sharing the Schrödinger equation. All you need to do is solve it. Of course, he was being a bit facetious, but the idea here is that you don't need to memorize things. What you could do is learn the fundamental principles of physical chemistry first, like thermodynamics and kinetics, and then try to understand organic chemistry from that point of view is a lot more powerful and empowering for students. And that's something that I'm planning to do using, of course, programming, using software that helps you figure out reaction mechanisms automatically, like what we have as a preprint in ChemArchive. So I really am going to push for a more computer-driven approach of learning and teaching. But I don't, I just don't think that certain areas will all of a sudden disappear. They will evolve.
Very clear. Very clear. Thank you. So we got no questions from the YouTube audience. And so without question from YouTube, I'm going to close this seminar. And let's thank again Professor Gabriel. Congratulations. Wonderful results and very nice presentation.
Thank you. Thanks for having me. Obrigado pelo convite. Foi muito legal. Muito obrigado.
Muito prazer. Até a próxima.
Um abraço. Valeu, Gabe. Tchau, cara.